All right, awesome. We're all here, so I'm going to get started. OK, so last time we talked about constraint satisfaction problems and the potential connection between proving hardness of approximation results for them and designing great tests for the property of a function being a dictatorship. And we mentioned that Håstad, whose work we're going to talk about today, showed a strong connection between these two things, and particularly showed that it suffices to get hardness results to prove and analyze a certain relaxed kind of dictatorship test. So I want to spend a few minutes talking about what this relaxed condition that's going to get involved in the picture is. So I'll make a definition related to something that came up when we proved the KKL theorem. And it's sort of a variant of the definition of the influence of a coordinate on a function. So if I give you a Boolean function, let's say into the reals, and some sort of noise parameter, rho, we'll say the rho stable influence of coordinate I on F is, I'll write the influence with this superscript parentheses rho of F. And that'll be defined, well, I can give one of two definitions. It's the noise stability of the ith derivative function. That's some kind of combinatorial definition, I guess. Or I mostly just think about the formula, to be honest, which if you apply the Fourier formulas we know to this, you'll get the following. OK, so take a look at the second formula just for a second. You see, if we deleted this rho thing, or if rho was 1, that's like the case of no noise, then we just get the sum of the squares of the Fourier coefficients on sets containing I, which is the normal influence. OK, but this definition sticks this exponentially decaying factor in here. Don't be overly excited about the -1. It's not a big deal. This exponentially decaying factor, which sort of attenuates the contribution from really large sets S. OK, so by contrast, as we're going to see in a second, although let's say if f is the parity function where every coordinate has maximal influence 1, actually if rho is some number between 0 and 1, then all of the rho stable influences for parity will be very small. And as long as we've made this definition, let's also define the total rho stable influence just to be the sum of these things, just like we do for the normal influences. We'll use the same notation. OK, and if we, let's say, sum up this formula and then interchange the sum, we'll get like a factor of the cardinality of S coming in. So this would be the sum. This k goes from, I guess, 1 to n of k times rho to the k minus 1 times the weight at level k. OK, again, if we just have the total influence without this noise, this would be 1, and you get the sum of the weight at level k times k, which is an old formula of ours. OK, so this quantity doesn't have like a super awesome combinatorial interpretation. It's kind of like you do the experiment in influence, where you pick a random string. Let's say if f is Boolean valued. You pick a random string and flip the ith coordinate and ask if that changes the value of the function. Now it's more like you've changed the ith coordinate, but also maybe you put some rho noise on the rest of the coordinates. But it's not exactly like that if you unravel the definition. So it's of medium interest combinatorially, but it's going to be a good like sort of technical device to talk about. OK, so let me just do a couple of examples or make some remarks. OK, so the rho stable influence of coordinate I on the dictator function, the ith dictator function, is still 1, just like it was before. And that's part of the reason we're happy to have this like a weird -1 here, because it keeps this property true. On the other hand, as I said, if you look at a large parity, let's say the influence of the ith coordinate with rho noise on, this is the parity of everything function, chi n, this is going to be rho to the n minus 1, okay? Because parity only has one Fourier coefficient at degree n. Okay, and if rho is strictly less than 1, then this will be some very tiny number. Another thing I want to point out, oh, okay. If f is a k junta, so it depends on at most k coordinates, well, the influence of coordinate I with rho noise on f is at least rho to the k minus 1 times the influence of coordinate I on f. Actually, that's just because this is true for any degree k function, because all the Fourier coefficients are at degree at most k. So this is just to say that if a function is a junta, like imagine k is not too big, then the influences and the rho stable influences are not too different. Oh, one more formula I wanted to point out. From this you see, remember the formula for noise stability is the sum over k of rho to the k times the weight at level k. So this is actually the derivative of that with respect to rho. So that's another kind of combinatorial interpretation of that quantity. Okay, let me make one more remark about this to try to give some feel for it. If you imagine fixing an f and fixing a coordinate I and cranking rho up from 0 to 1, this is clearly an increasing function in rho. And this rho stable influence of I on f increases, well, when rho gets all the way up to 1, it just turns into the normal influence again. And when rho is at its least value, 0, by the way, if you think about it, in this context, it's natural to use the convention 0 to the 0 is 1. So when rho is 0, then you only get the contribution from when cardinality of s is 1. So this is f hat I squared. Okay, so this rho stable. I'm knocking out the mic. This rho stable influence goes between the degree 1 Fourier coefficient squared and the total influence. Okay, any questions so far? All right, so the main technical utility of this definition is that it's a very good way to pick out the coordinates of an arbitrary Boolean valued function that are somehow notable or important for that function. Naturally, if it makes sense to say that if a coordinate has large influence on a function f, then it's somehow notable. But that's not so satisfactory, because if the function is like the parity function, then every coordinate has gigantic influence. And so, I don't know, it's not so noticeable if given coordinate, or notable somehow for the parity function, since everything is the same. So this theorem is very simple, but I'll give it the status of the theorem because it's important. It just says that if you have any, let's say, Boolean valued function, it has at most a constant number of coordinates which have large stable influence. Okay, so to make that more precise, let's say that f, well, I may as well let it go into R. I'll just need to assume that its variance is at most 1. But you should think of f being, let's say, a Boolean valued function. Now, for any parameters, epsilon and delta, let's let J be the set of, let me call them notable, or I'll even say epsilon, delta, notable coordinates. Namely, all those whose 1 minus delta stable influence is at least epsilon. Okay? So all the coordinates that have kind of large influence, once you add a little bit of noise into your definition of influence, then J is not too big. Okay, so in light of this, once we prove it, it's easy. You see we have like a nice way of sort of picking out the important or notable coordinates of a function. And it'll have the property that, as you might hope from the terminology notable, you don't like pick out all of them. That'd be kind of silly. You prefer to err on the side of picking out no coordinates if none seem particularly special. Okay, so this proof is very easy. So the first observation we'll make is that, the total, the cardinality of J is certainly at most the total influence divided by epsilon. Okay, because every coordinate in J has this much 1 minus delta stable influence, and this capital I represents the total. These are all non-negative. Okay, so it suffices to show that this quantity is always at most 1 over delta. Okay, so here's the formula for that. It's some kind of linear combination of the weights of f. And if you remember, we're assuming that the variance of f is at most 1. And this variance is the sum as k goes from 1 to n of just the Fourier weight at level k. Okay, so to show this, in light of this formula, it suffices to show that each of these coefficients is not too large. K times, we're choosing rho to be 1 minus delta here, for all k at least 1. People agree to that? Okay, but this is like some exercise in arithmetic. So here's one way to see it. This thing is equal to 1 plus 1 minus delta plus 1 minus delta squared plus 1 minus delta cubed, etc. It's a geometric series. And this thing is, it's just, I can write down 1 minus delta to the k minus 1 k times. And this is k times. But now I claim the right-hand side is obviously at least the left-hand side, because each of the first k terms here is at least 1 minus delta to the k minus 1. So it works out term-wise for the first k terms, and then this just has even more stuff. Okay, so that's the end of the proof of that. Any questions? Okay, so getting back to dictator tests, dictators are the functions from here we know that have a stable influence even equal to 1, the largest possible. And what we're going to go up against is not just the functions that are, or not all of the functions that are sort of far from being dictators, but just the functions that are very unlike dictators in the sense that they have no notable coordinates at all. Okay, and this notion of a function with no notable coordinates is a very important one. I used to sometimes, I still do in my head, equate this with some kind of notion of quasi-randomness for the function f. But this term already has like a lot of meanings, so I didn't want to step on it too much. But it's at some level like a function that has, no one coordinate really influences the function too much. Let me also remark that, well, I'll come back to that in a second. Okay, so what are some good examples of functions that have think in your head of like epsilon and delta as being like 0.01, just very small constants. So what are some functions that have no notable coordinates? So some exemplars here are the parity function. You know, all of its 1 minus delta noisy influences are, you know, exponentially small. So in fact, any large parity has no notable coordinates. Yeah, a constant function is an excellent. That's another reason why it's like arguably questionable to call it by this name. Constant function doesn't seem too random. But a constant function is a great example. Yeah, majority is another good example. Majority has the property that all of its just normal influences are very small. They're like 1 over root n. So certainly the sort of row stable versions are going to be only smaller. And constants are the ultimate example. I mean, all their noise influences are 0. OK. And that corresponds sort of to the notion of that these guys do not have any notable coordinates. Sort of the anti-exemplars, or the functions that do have notable coordinates, are, well, as we've seen, dictators. And also in light of this observation, I would like to say, you know, juntas. Let's say O of 1 juntas. Although there's a very slight catch with this. You have to say that are not constant. OK, if it's a constant function, it's certainly a junta, but it also has no influential coordinates. But if it's a junta and it's not constant, then it's, you know, its bias is some non-trivially positive amount. And so every relevant coordinate will have at least a little bit constant amount of influence. I should also just want to add that this sort of concept gets stricter as you make epsilon and delta smaller. OK, as you make epsilon and delta smaller, let's see. If you make epsilon and delta smaller, I want to say fewer and fewer coordinates will have small 1 minus delta stable influence. OK, questions? All right, so that takes us back to where we were having, you know, taken this somewhat tangent. That takes us back to where we were last time when we were talking about CSPs and dictatorship testing and hardness and the connection between these things. So when we saw last time that, you know, the PCP-P theorem implied a sort of slight hardness of approximation result for 3 sats, and we kind of intimated that the thing that prevented you from getting a really good hardness of approximation factor was that the dictator test component needed to have a large rejection rate. So this work by Bellari, Goldreich, and Sudon sort of suggested that from, you know, dictator tests, if you applied some appropriate PCP technology, you could get some hardness of approximation results. And sort of the great idea of Håstad in this PCP area was to show that this is even true if you have some kind of relaxed dictator test. OK, so now I want to properly define what I mean by this relaxed dictator test. OK, so let me call this dictator versus no notables test. So this definition has a lot of parameters, so bear with me. OK, so imagine you're trying to prove hardness of approximation for a certain kind of CSP. So CSP has a set of predicates, capital Psi. And for simplicity, we'll assume that we're working with CSPs that have the domain that's just bits. Okay, although actually everything works fine for larger domains. Let alpha and beta be two parameters between 0 and 1. So these are going to be the hardness result that you're shooting for. So one designs these tests with the idea of proving that it's hard to alpha out of beta approximate the CSP defined by this predicate set. There'll be one more condition I'll come back to in a second. Okay, suppose for all natural numbers n that there exists a local tester for functions on n bits satisfying. I guess this definition is going to have to go to a second board. Be a right to left definition. Okay, so first condition is that the same condition for a normal local tester for dictatorship, that a dictator should pass the test with high probability. So normally we insisted on passing with probability 1, but we're going to relax this a little bit to just beta. So we want that if f is a dictator, then the probability that the test accepts f is at least beta. Okay, so you can think of beta usually as 1 or close to 1. And on the other hand, we don't need to reject functions that are close to dictators or a little bit far from dictators. We just want to reject the ones that have no notable coordinates. So let's say f has no. For simplicity, I'm just going to set the parameters to be the same thing. I want to say in this case that the test accepts with much lower probability, namely alpha. I want to say at most alpha, but we're going to allow you to have a slightly larger probability, assuming epsilon is small. This is kind of like sticking the rejection rate in a different place. So I'm going to say plus lambda of epsilon, where lambda is a function such that lambda of epsilon goes to 0 as epsilon goes to 0. Okay, so this is just some sort of like little o of one term that gets small when epsilon gets small. So this is actually kind of like a sequence of statements. You know, as you make this condition stricter and stricter, so that you're saying f has no notable coordinates and it really has no notable coordinates, sort of the probability the test accepts should kind of go towards at most alpha. And finally, what do the predicates have to do with anything? We just need that the tester, when viewed as a CSP, remember last time we saw that a tester, a string tester, and a constraint satisfaction problem are the same object, uses predicates from the set psi. Okay, any questions about that so far? It's just that, well, I didn't really finish this sentence, but suppose this exists, then we call, really this is slightly annoying. Really this is a family of tests, one for each n, but we're just going to say if this exists, we'll say we have an alpha, beta, dictator versus no notables test using psi. No, so this is really like for all epsilon. Okay. And it's very important, by the way, that this thing doesn't depend on n. Okay, it doesn't. I mean, I said it exists here before I let n exist, but the key is that it's some function only of epsilon, and it goes to 0 with epsilon. How slow, it doesn't really matter to us, but it shouldn't depend on n. Okay, so this definition, I know, is a little bit to wrap your head around. We will see an example of it today. So it's like a local test for dictatorship, only a little bit different. But what it's good for is that if, as soon as you design and analyze a test like this, you immediately can get a hardness result for the associated CSP. So back in like 97, when Håstad was doing this stuff, he showed that if you have something that's like more complicated than this, I can't even write down the definition, it's very complicated, but if you have that, then you can get an associated or an analogous NP hardness of approximation result. Okay, and then like 10 years later, it was determined that if you're willing to accept this conjecture in complexity theory called the unique games conjecture, then you just need to build this thing to get a hardness result. So that's what I'm going to tell you today. So here's the theorem. Fix a CSP over domain equal to bits, although, as I said, all this stuff kind of works for any domain. And suppose there exists this object. As on the right board. Then, for every constant delta greater than 0, it's, let me say, UG hard to alpha plus delta out of beta minus delta approximate the CSP. Okay, so let me remind you what these things mean. UG hard, it means NP hard if the unique games conjecture is true. Yeah, if you don't care about this stuff, just it's hard assuming some complexity theoretic conjectures. There should be no polynomial time algorithm. And to remind you what this means, it means that this is the task. I give you an instance of the CSP, and I promise you that the optimum solution satisfies a beta minus delta fraction of the constraints. The task is to find a solution satisfying at least an alpha plus delta fraction of the constraints. Okay, so if you kind of, for a second, ignore these little plus and minus deltas, it sort of exactly says that as soon as you have one of these dictator versus no notable tests, and the test, when viewed as a CSP, uses these predicate psi, then you immediately get hardness with these two parameters. Okay. And to say like one word about why that's true, this test, it really is an instance of the CSP that you're trying to prove hardness for. And you can use it as a gadget in a NP hardness reduction from the UG problem, which is conjectured to be hard by some, to produce these hard to approximate instances of the CSP. So actually, we're going to more or less see the proof of this theorem in 1 week on Monday. But for now, we'll just take it for granted. OK, any questions? OK, so what's great about this setup is that now if you want to be a person that proves hardness of approximation results, you don't need to know anything about PCPs or unique games or anything about computational complexity. You just have to know some Fourier analysis. I mean, you just have to design and analyze dictator tests that have these properties. OK. In the interest of not telling lies, technically, there's some tiny conditions which I don't even want to mention, but I will mention them here. First, actually, your test, this should all work. for not just Boolean valued functions, but functions into the real interval -1, 1. So I didn't even want to say what it means to test a function whose values are not plus or minus 1, but whose values are in this range. It's kind of like testing a randomized function. Okay, I don't really want to say more, but in the interest of telling the truth, I have to add that to this definition. And also, this is super technical, but this makes you more unhappy. This makes you slightly happier. It's OK if the tester queries the same string more than once. I can't believe I'm even saying this, but like theoretically, according to our definitions, in a CSP, whenever you apply a constraint to some variables, they should be to distinct variables. But we did not have this condition on a tester. A tester could, query the same position more than once and apply its predicate to it. So as I said, I can't believe I'm mentioning this, but that's actually OK for the purposes of this theorem. OK, so what are we going to do for the rest of the class? We're actually just going to basically build one of these guys and deduce a hardness result for Håstad's hardness result for approximating linear equations mod 2 with 3 variables per equation. OK, so actually many hardness of approximation results based on the unique games conjecture and also NP hardness ones work on this principle, and I'll tell you about 2. So the following theorems are both due to Håstad, although he didn't use this exact terminology. So one is about 3 SAT and one is about 3 LIN. So first of all, for all, I want to say delta between 0 and 1/8, there exists a 7/8 plus delta versus 1, dictator versus no notables test using, or of 3 literals predicates. Okay, so it's a tester. It takes an unknown Boolean function. It queries it at 3 places. It makes its decision to accept or reject based on the or of some possible negations of the outcomes. It accepts dictators with probability 1. And basically, if it accepts any function with probability noticeably bigger than 7/8, then that function must have some notable coordinates. OK, that's the 3 SAT one. The 3 LIN one is as follows. For all delta, I don't know what bound I need here. I guess less than a half. That's not a big deal. There exists a half 1 minus delta test using 3 variable linear equation predicates. This is in F2. OK, so it's a similar, well, it's another 3-query test that distinguishes well between dictators and functions with no notable coordinates. Yeah. OK, so if we just plug these Fourier theoretic statements, or these property testing statements, into this theorem, we immediately get statements that look like Håstad's famous NP hardness of approximation results that I stated last time. They're actually just a little bit worse. So as corollary, we get that for all delta greater than 0, if we do the first one, it's UG hard to 7/8 plus delta out of 1 minus delta approximate max E3 SAT. That's the name of the CSP that uses this kind of predicates. And for the second one, we get that for all delta greater than 0, it's UG hard to half plus delta out of 1 minus delta approximate max E3 ln. Okay. So as I mentioned last time, this is actually a little bit worse than what's known. So Håstad got some stuff that's a bit better. First of all, he made both of these things NP hard. Okay, so that's really hard according to standard assumptions, whereas this corollary only gets you NP hard. So to do that, he had to do something much more complicated than this. And the other deficiency here is Håstad got rid of this, which is nice from an aesthetic point of view. You see, he showed that even given a 3-SAT instance, which is perfectly satisfiable, there's a satisfying solution, it's still hard to satisfy more than a 7/8 plus delta fraction of its clauses. Okay, and we did not get something quite as strong here. We get the sort of analogous results on the testing side. We have a 1 here. But this unique games theorem has a property that you always lose like a small delta on this side. So that's a slightly annoying deficiency, but we're going to deal with it, or live with it today. See, for 3 ln, we actually don't mind losing this little delta here. Our test is already losing a small delta anyway. And furthermore, we know we could not possibly hope to prove this result, that it's hard, given a perfectly satisfiable 3 ln instance, to satisfy more than a half plus delta fraction of the constraints, because we know it's not hard. There's a polynomial time algorithm given a perfectly satisfiable system of 3 variable linear equations to find a perfectly satisfying solution. Okay. Okay, so for the rest of the class, I want to prove this thing. Okay, so once you believe this theorem that we'll prove on Monday, this will tell you how to get really this hardness of approximation result for E3 ln. Okay, so let's talk about these kind of complicated and scary-looking objects, the dictator versus no notables test. So whenever you're trying to prove a hardness of approximation result like this, you know from this theorem what kind of parameters you want your test to have. So there's 2 components to what you need to do. There's design and analysis. And both of these are, interesting and, take some thought. So in other words, you have to actually think up like a clever test that has this property. And, that will take some thought. And then you actually have to prove that it has these properties, and that will also take some Fourier analysis and thought. Okay, so let's start with this problem and think about the design question. Okay, so the first thing is we know we want to prove a hardness result for the CSP with these kind of predicates. So that tells us sort of what our test has to look like. It's got access to some unknown Boolean function. It's kind of trying to test if it's a dictator or not. And we know what it should do is query the function in 3 places, and then accept or reject based on some statement that looks like f of x plus f of y plus f of z equals either 0 or 1 mod 2. Okay, so the test has to look like, choose x, y, and z in some clever way, and really that's the key to the design. And then we're sort of, our hands are tied. We have to accept or reject based on something that looks like this. Okay, and we want to sort of pass with high probability only if the function is a dictator. So what are we going to do? Well, the first idea that may come to mind, I mean, if you're trying to put this in the context of stuff we've done before, we do know one test that looks a lot like this. Okay, you could start with the BLR test. The simple test we saw in lecture 2 for trying to test if a function is a parity, a linear function over f2. So the good thing about that test is it definitely has this property. In fact, it always tests whether f of x plus f of y plus f of x plus y equals 0 mod 2. Okay, so sort of so far so good. But of course, we're not done. I assume you remember that 2-page definition, no problem. Okay, so let's look at the pros and cons of what we got so far. Okay, so the pros is that it uses the right predicate for its test. Okay, that's good. That was bullet number 3 in the definition. Bullet number 1 was that you accept dictators with probability at least beta. So the beta we're shooting for here is 1 minus delta. You should accept dictators with probability at least 1 minus delta. Actually, we're doing better than that. This accepts dictators with probability 1. Okay, because every dictator is a Boolean parity function, and we know that BLR test accepts parity functions with probability 1. So that's good. So let's move on to the cons of this test. Well, the point is it's supposed to accept functions that have no notable coordinates with really small probability, not much bigger than half. Okay? If the thing has no epsilon notable coordinates, it should accept it with probability at most half plus little o of 1 with respect to epsilon. But, well, any large parity also gets accepted with probability 1. Okay, and as we saw when we were making the definition, these large parities have no notable coordinates. All of their row stable influences are really small. So that's bad. They're supposed to be accepted with probability like around a half. And there's another category of functions that messes us up. The constant function 0, let's say in this context, is also accepted with probability 1. I mean, that's a linear function. Or you can just see, in the BLR test, you always test f of x plus f of y plus f of x plus y equals 0. So the constant 0 is also accepted with probability 1, and it's certainly got no notable coordinates. So these are two things we have to worry about in our design. Something that's neither a pro nor a con is that, smallish parities are accepted with probability 1. Okay, we don't care about that because it doesn't fall into like a category of functions we need to worry about. We only need to worry about dictators and functions with no notable coordinates. If you're the parity of x1, x2, and x3, then x1, x2, and x3 are going to be quite notable. So we don't care about that function. Okay, so we have these two hardships that we currently need to deal with, and we're going to fix each of them by making a little variation on the test. So the easier thing to fix is this problem that the constant 0 function gets accepted with probability 1. And here's the easy fix for it. I'll just sort of state it, and I won't even prove it because we'll prove something stronger later. But you can fix it by changing from the BLR test to what I'll call the odd BLR test. And it's very similar to BLR, but with a slight twist. So given f, for now we'll use this notation, f2 to the n into f2. You start like the BLR test. You choose x and y independently and uniformly. But now you also choose a bit b, just a single bit uniformly. Okay, and you set z to be x plus y mod 2 like before, but then you add b to each of the coordinates. Okay, so basically with probability a half, you set z to be x plus y, and with probability a half, you set z to be like the logical negation of x plus y. Okay, and then you accept if and only if. Now you query f of x, f of y, f of z, and you check if it equals b. So notice it's still okay. All of the tests, the predicates that this tester uses are of this form. Actually, before, we were only using predicates where the right-hand side was 0. We know that can never work, because then you would get a hardness result for the 3-variable linear equations with right-hand side 0. And that's not a hard CSP, because you can just set all the variables to 0. So now we're in better shape in the sense that we're using both the predicates that we allow. So let me explain to you why this fixes the first problem of the constant function 0. Well, actually, you can see right away, what's the probability that the constant function 0 passes this test? No. Half. Yeah, it passes if and only if b is chosen to be 0, so a half, which is good because I just erased it, but that's the sort of upper bound we're allowed. So actually, that fixes the function, although let me just say a little bit more than that. A dictator still passes with probability 1, or is accepted with probability 1. Right? If it's a dictator, if f of x is just xi, then this is xi, this is yi, and this is xi plus yi plus b. So this equation will always be satisfied. Okay, 0 passes with probability a half, as we just saw. And in general, if you do the Fourier analysis, I won't do it, but you could all do it. Let me switch notation now to -1, 1. The probability that the odd BLR test accepts any old function f is, okay, this is the probability that the BLR test accepts, if you recall from so long ago. It's basically the sum of the cubes of the Fourier coefficients with this half plus half. And for the odd BLR test, you get the same thing, only you only sum over the sets of odd cardinality. Okay, you can check that that's consistent with these two facts. And, well, that's all I'll say. Okay, any questions so far? Okay, so this test is good, and we've got rid of this con. And we've got rid of half of these cons. You see, if you're a large parity of even cardinality, then this thing will be 0. So you'll accept it with probability a half. That's what we're shooting for. But if you're a large parity of odd cardinality, then one of these coefficients will be 1. So you'll pass with probability 1. Okay, so we still have to get rid of those. Okay, so this is where Håstad's good idea on the design front came in. His idea was to take this test and insert a little noise into it. Somehow, like something very lucky is going on for a large parity, because z is equal to, I mean, forgetting about b for a second, it's equal to x plus y in like every coordinate. So if it was wrong in like a few coordinates, then that wouldn't really affect likely wouldn't affect the probability that a dictator passes, because the dictator only cares about one coordinate. But if you add like a little bit of noise, it will completely break the fact that large parities are accepted with probability 1. That was not a really great explanation, but let me just say something different instead. So this is Håstad's idea. Fix some delta greater than 0. And in this odd BLR test, replace z with some string z prime, which is basically the same as z, but with a little bit of noise. So this notation, if you remember, means z prime has correlation 1 minus delta with z. So it's the same as like flip each coordinate of z with probability delta over 2. Okay, so take this z, but right at the last second, before using f of z, flip each coordinate of z with some small probability. So what effect does this have? Okay, without doing the analysis, let's think it over from a design perspective. From what effect does this have on the cases we worry about? So if f is a dictator, well, really this was passing because of this fact, and this will still be true as long as zi equals xi plus, as long as z prime I equals xi plus yi, which almost always happens because for each coordinate you rarely put noise on it. So if f is a dictator, it'll be accepted with probability 1 minus delta over 2. It'll be accepted if and only if you did not put any noise on the dictator's coordinate. Okay, and at a high level, somehow if f is a large odd parity, well, somehow adding this noise will like kill the, I don't know, the correlations or something. I mean, each noisy bit that goes into the parity will like flip the parity of the parity of z prime. So, kind of, if you have like a constant fraction of bits in there, that's going to make f of z prime, or the parity of z prime, totally uncorrelated with the parities of x and y. Okay, we'll see that more precisely when we just do the analysis. But what I'm saying is, if you think about, imagine f is really the parity of everything. We're doing z prime here. And let me, for simplicity, imagine there's no b. Okay, so we're just testing 0. Well, it's true that the sum of the bits mod 2 in z is equal to the sum of the bits mod 2 in x and y. But if you start like randomizing a delta over 2 fraction of the bits in z, this equation is probably going to hold with probability about a half. Okay. So all of this is to lead us to give Håstad's final test. So Håstad's test is parameterized by some delta, and we'll call it the Håstad subdelta test. And let me switch to plus or minus 1 notation for good here. So given access to a Boolean function, we're going to choose x and y independently as before. And we're also going to choose a uniformly random bit as before. And we're going to set z to be x plus y, or now we're using plus or minus 1 notation. So this is like the component-wise product of x and y. And then we're going to set z prime to be this noisy version of it, delta noise. And then finally, we're going to accept if f of x, before we would have written this, if we were writing mod 2. But now that we switched to plus or minus 1 notation, these just become times. Okay, sorry for this annoying, there's no way to get around it, this annoying switch back and forth between f2 to the n and plus or minus 1 to the n. Okay, so although it doesn't look like it, this is applying a 3-variable linear equation mod 2 predicate to the outcome. You have a question?
Should B be in
Oh yeah, excellent point. Thank you. Z should be B times this. Yeah, because before it was x plus y plus like the constantly b vector, okay? So now it's like you either want to take x times y or x times y negated, depending on what b is. Okay. All right, so we finished actually the design stage. And now we have to move on to the analysis stage. Okay, so here's the theorem that essentially I promised you. So this is a half comma 1 minus delta, actually over 2. Dictator versus no notables test. Okay, using these 3 LIN predicates. Okay. And actually, for future reference, I will even specify that lambda function, although usually you kind of just do that at the end. Lambda of epsilon is half root epsilon if epsilon is less than or equal to delta, and half epsilon is bigger than delta. Actually, just because probably you forget what all this means now, this comes into the second thing. We'll need to show that if f has no epsilon influential coordinates, we want to show that the test accepts with probability at most this thing, a half, plus this thing. Okay, and the form here is not so important as long as it's something that goes to 0 as epsilon goes to 0, which it does for each fixed delta. Okay. So the first thing we're going to do is just sort of the same thing we do whenever we have any of these tests. We'll just write down exactly a Fourier expression for the probability that a given function f passes this test. Okay, so here is the claim, which will be most of the work. Well, some of the work. Probability that Håstad's test with parameter delta accepts a given function f is equal to, well, it's very similar to the thing for the odd BLR test. So that half plus a half, the sum over all sets S of odd cardinality of f hat S cubed, but with this extra factor, 1 minus delta to cardinality of S in there. Okay, and that's exactly what's going to sort of, for example, kill the large odd parities, i.e. make them pass with probability close to half. See, this will be close to 0. Also, we're going to prove this, and if you set delta to be 0 in this claim, then this piece goes away, and there is no noise, so you just revert back to the odd BLR test. Okay, so we're actually even implicitly going to prove the claim about the success probability or passing probability for the odd BLR test. So you no longer have to do that exercise. Okay, so here's that proof. Well, it's pretty easy. It's just like the BLR test and the noise stability stuff combined. So let's first, this B thing is a little annoying. So let's first assume that in the test you did, B turned out to be plus 1. Okay, that's like back in the BLR test, there was no B. Okay, so I want to compute the probability that F is accepted conditioned on B equals 1. Okay, so when b is 1, well, you're testing whether the product of the three things is 1 or not. So it's see, this quantity is 1 if their product is 1, and it's 0 if their product is -1. So this is the expectation of the indicator of the acceptance condition. Okay, so now we'll just start doing all the Fourier stuff. So let me take out the halves by linearity of expectation. And really, once we're conditioning on b equals 1, the only random list left is x and y. Okay, so it's the expectation over x and y, f of x, f of y. And once you have x and y, z is defined. Okay, it's just x coordinate y is multiplied with y, in this case, when b is 1. But we still put some noise to get z prime. So I want to say that this is the expected value. I'll put that noise in here of f of z prime. Okay. Now, can somebody tell me what this thing is in terms of a familiar operator? Somebody said it. Who was it? Every time I look away, somebody whispers. Let's see if I can get them to get it. It didn't work. Okay, this is z prime is drawn from to be a noisy version of z here. So this is t 1 minus delta of f at z. Okay, if you remember from those homework so long ago, this is the definition of this t operator. Once you apply it to f, its value at a string z is like the average value of f on noisy versions of z. Okay. Great. Let me just readjust it again. First, I'll pick x, and then I say, at this point, I know what f of x is. And then I'll pick y. And then I say, I know what f of y is. And this thing is f at z is nothing more than, x component-wise multiplied by y. Okay? You okay with that? Okay, so think back all the way to like lecture, I want to say 2, and tell me what familiar less symbols thing this quantity is. It's been a long semester, I know. Okay, we have two functions, f and this other function, and we're doing something like their inner product. We're taking expectation of y of f of y times this function, not at y, but y like twisted by x. Yeah, it's convolution. You know, back when we were doing convolution, we usually did all our domains being f2 to the n, and this was plus, but we switched to plus or minus 1 notation. So in convolution, this is like component-wise multiplication. That's a plus. Good. So this is a half plus a half expectation over x, f of x, times a certain convolution at x. You see, it's f convolved with t 1 minus delta f at x. All right. Good. So now what do we have? We have something that really is like the inner product in our lecture 1 days. We have two functions, this function f and this crazy function. We're just taking the expected value of f times that function, both at x. So we used to write that as half plus a half, the correlation of f with this function. This marker's not so hot. Okay, and now we're going to use, what are we going to use now? Yeah, Parseval or Plancherel or whatever. So we have the expected value of the product of two functions. We know it's like the sum of the product of the Fourier coefficients. So it's the sum overall s, f hat s, that one is easy, times f convolved with t 1 minus delta f hat s. Okay, and now we know that convolution, that Fourier transform of a convolution is like the product of the Fourier transform. So this is f hat s. This is t1 minus delta f hat s. Okay, and this thing has the effect of multiplying the s Fourier coefficient by 1 minus delta to cardinality of s. So I think this is the last step. This is, sort of. Half plus a half times sum over s 1 minus delta to cardinality of s times f hat s cubed. Okay, so if you remember way back to lecture 2, this is really the same thing we did when analyzing the BLR test, except with the addition of this t1 minus delta is thrown in there. Great. So are we done? No, because we assume that b is 1, and these two things are not the same. But can I erase this now? I guess I can. Oh, I better not erase it yet. Okay, but, well, half the time we get this. Half the time we get the same thing with b equals -1. So what happens if b equals -1? Well, then we test that f of x, f of y, f of z prime is -1. So this thing will be the same, only this will be a minus. Okay, so first you'll get the expected value of half minus half f of x, f of y, f of z prime. Okay, so these will all be minuses, minus, 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 minus. And the other difference is that z prime is no longer, z prime is like a noisy version of the negative of x composed with y, or times y. Okay, which is the same, actually, as z prime is distributed as the -1 minus delta noise applied to x plus y. Okay, because as we saw a million years ago, negative noise is the same as like first negating the string and then doing noise. Okay, so that means everything will be the same here, except everywhere you had t 1 minus delta, you'll have like t -1 minus delta. So you'll get this. Okay, so then therefore this will eventually be half minus half sum over s minus 1 minus delta to cardinality of s, f hat s cubed. Okay, so the probability of passing when b is 1 is this thing. Probability of passing when b is -1 is a similar looking thing. And we do each of these two things with probability of half each. So the overall acceptance probability is the average of this quantity and that quantity, which is this. Okay, you get the same half, and then for all the even cardinality s's, you get this thing and this thing have opposite signs, so they average to 0. And for the odd cardinality s's, you get the same sign. So it averages to this. All right. This is like an 80-page paper, by the way. But it included all sorts of great stuff in addition to this. OK, any questions? All right. Great. So we're almost done. Now, let's see. Let's erase some things. let's erase this. We have the claim about the probability that the test passes. And now we just want to prove the theorem. Okay. Okay, so there are three things to check in the definition of a dictator versus no notables test. Two of them are easy, so we're supposed to check that it uses the right kind of predicates, which it does. And we need that dictators pass with probability at least this. And that's easy to see in two different ways. One, it's kind of clear from the definition of the test. And it's also immediate from this formula that we found. If f is a dictator, then maybe f hat I is 1. So you get half plus half times 1 minus delta, which is this. In fact, we have equals here. OK, so the main thing we have to prove is this final condition that says if f has no epsilon epsilon notable coordinates, i.e. all the 1 minus epsilon stable influences of f are at most epsilon, then the probability that the test accepts f is supposed to be at most this number, plus some term that goes to 0 with epsilon, which will be this lambda epsilon. OK, another way I should have said this earlier, but another way to look at this condition, it's very much like saying f has no large, it's not quite the same, but it's similar to saying that f has no large low-degree Fourier coefficients. And there's one-way implication. You see, if this is true, f has no epsilon epsilon notable coordinates, then it will have no large low-degree Fourier coefficients, except possibly the empty coefficient. Because this thing, remember, is sum over s containing I, 1 minus epsilon to the cardinality of s minus 1, f hat s squared. So if you had some large low-degree Fourier coefficient, this number would be large for an s which was not that big. And so overall, it would give you some big number. And similarly, you may hope that if that's the case, then indeed this thing will be small, because it sort of seems that the only way this can be large, and that's exactly what we'll show in a second, is if you have some large low-degree Fourier coefficient. OK, so to prove that claim, OK, this proof is of this claim, but we're just going to use this claim. Well, this is the probability that a test accepts any function f, and we'll do the same trick we always do in the BLR test, which we'll write this as, we'll say this at most. We'll take out 1. OK. We'll take out this 1 minus delta to the s and 1 copy of f hat s and maximize over it. And we'll leave the rest, which is 2 copies of f hat s, inside the sum. OK, and by Parseval, we know that this thing is at most 1. OK. So we need to show that this thing, this max, is smallish, sort of at most this lambda, getting to assume this condition. OK, and now it's just a little arithmetic. OK, so if I have the max of a bunch of numbers, and then I square them, let me put absolute value in here. That's OK. If I have the max of a bunch of non-negative numbers, and I square them, and take the max of that, then it's like the square of the original max. That was a confusing sentence. Well, anyway. I just squared the inside and then took a square root on the outside. That commutes with doing the max. Pardon me? No, I don't want to use Parseval again, but I want to make something that looks like this. Because I want to show that this whole thing is small, and I want to use this condition. This was for all I. OK, so now this thing is almost the same thing as it's in here, except that here I have cardinality of s minus 1. Here I have 2s. But that's OK. This is a number less than 1. I'm raising it to the power of the 2s. It'll only get bigger if I raise it to the power of cardinality of s minus 1. OK, and now I want to actually say that this maximum has to be small, smaller than epsilon. Because suppose this thing is, I'll say in words, if this thing is bigger than epsilon, this term will literally appear in all of these 1 minus epsilon stable influences of I for any I that's in the associated S. Actually, it'll appear at any time. So therefore, that's at most, well, the maximum over I in N of this noise stable influence. Now, actually, in doing that step, I made like a little hidden use of one assumption here. I used the fact that S was odd. Can somebody tell me how? Right. I needed that to be not empty. So in the empty set case, this does not contribute to anything. Well, actually, this doesn't even really make sense, actually. Well, this makes sense, but this step doesn't even make sense if you consider the case of S of cardinality 0. Okay, so here, actually, I was already relying on the fact that by virtue of S having odd cardinality, it has cardinality at least 1. But in particular, you know, this contributes to any stable influence that's in S. OK, and this, oh, sorry. This is the 1 minus delta influence. And this is at most half plus half roots epsilon by assumption if epsilon is at most delta. See here, my test involved this parameter delta, but my condition on the influence involved epsilon here. But this influence is only larger if I make epsilon smaller. OK, so once epsilon gets smaller than this fixed constant delta, I have this bound, which is why it goes into here, and it goes to 0 as epsilon goes to 0. So that's it.